Thank you. Thank you very much. Hi, everybody. I am Michael. I work at Imperial, and I'm going to talk a little bit about this new numerics package that we've developed for optimized finite difference computation from symbolic equations. And to motivate this talk, I want to start a little bit by looking just at the way we write solvers for partial differential equations. So, and for this, I'm showing here the simplest equation that I could find, really. First order diffusion equation in 2 dimensions, discretized with a simple finite difference stencil. And if you know a little bit about finite differences, you know that this is like the classic 5-point star stencil, and you can write this in a few lines of Python. And that's pretty easy to do. But as soon as I want to do something more realistic, something that we actually use in our research, I just increase the complexity of my equation a little bit and go to like a 3-dimensional wave equation with a slightly higher stencil discretization, something like 12th order. I get this type of code. And this is much more complex and obviously much more error prone to actually write this by hand, to getting all of these minuses right in all these places. So this really is a problem that spans industry as well as academia, because when people write these codes, this is still a fairly moderate example. This takes a lot of time to get right. It takes a lot of time to then verify that it is right. And then I want to run this on an HPC hardware, because whenever I use these stencil algorithms, I really need performance. So I need to do some more stuff to actually make this run, possibly on something like accelerator architectures. And it's a huge expense of time and money, effectively. However, if I want to do innovation at a higher level, at a mathematical level, at an algorithmic level, where I use these solvers kind of as black boxes, if I'm interested in different solving strategies and inversion algorithms, this really comes back to bite, because if I need to change just a little bit here, like the stencil discretization, I want to move from 12th order maybe to 16th order, that'll take me weeks to re-implement. And that's a real productivity bottleneck that we have, because that means that effectively it can take up to several months for good, innovative algorithms to actually hit production. And that's a bad state to be in. The most frustrating thing about this problem is that we actually know how to solve this. And the idea to approach this is really through symbolic computation. So in this paradigm, we create domain-specific languages that provide really high levels of abstraction, especially for our mathematicians, numericists, and domain scientists. So the idea being that these guys have to write code that isn't actually solving the equation, but that actually defines the mathematics, code that's much closer to the PDE itself. And we can then use automated code generation to actually create these really complex, low-level kernel codes that we actually need to solve the problem. And this type of approach creates a separation of concerns between the numericists and the domain scientists, who can now think about algorithmic improvements, about using different discretizations, different formulations of an equation, and the computer scientists, the compiler gurus, who really know how to make these things fly in a particular architecture. Because everyone is now working to a mathematical spec in the middle, and we automate things at runtime. And we want to use this approach for high-performance kernels in seismic imaging in my group. So seismic imaging is one of the really, really challenging problems in HPC. It's a very large-scale inversion problem. It has huge amounts of data. This is effectively a really good example where big data means big compute. And in fact, some of the largest privately owned supercomputers in the private sector are actually just bought for this type of algorithm. So you really need to make sure that the solvers and these kind of kernels that you want to run on there are highly, highly optimized. Now, for various algorithmic reasons, a lot of people prefer finite differences here. There are other packages that can do this kind of high-level symbolic approach, like maybe you've heard of things like Phoenix or Firedrake, that have proven that this approach can work. But for most practitioners, they still prefer finite differences. So what they end up doing in reality is writing these horrible, horrible stencil codes by hand. Wouldn't it be great if we could automate this process and make everyone more productive? Well, we can. And in fact, there's a wonderful tool in the scientific Python ecosystem that allows us to do just that, SciPy. It's a complete symbolic computer algebra system in pure Python that allows me to do just that. It allows me to programmatically and in an automated fashion create, manipulate, and build mathematical equations. In fact, they provide us with all the kind of tools and utilities that we need. We can express functions, we can express derivatives, we can Taylor series expansions, all the kind of things that we need to actually generate these complicated stencils. And there was a wonderful tutorial on Monday where they even showed that they can do code generation and generate low-level, fast C and Fortran code. So that's really great. But for these extreme high-performance cases that I'm talking about, that's not quite good enough. Because these are really specialized domains. Stencil computation itself is an active research field in the computer science, in the compiler community. And there are many more tricks that you can do than just writing C code for it. And this is why we built Devito. Devito is a finite difference DSL that's completely based on SciPy. It uses SciPy to auto-generate these low-level stencil expressions and then optimizes them in the process using all the kind of research from stencil computation research, yeah. So the idea is we do all the kind of usual tricks, OpenMP threading, vectorization pragmas, loop blocking to ensure data locality, auto-tuning for particular architectures at runtime. We can even do some more advanced stuff like symbolic stencil optimization through the power of SciPy, where we effectively try and reduce the number of flops, the number of operations that we actually need to compute for each stencil point. Because we know the specific domain we're computing, so we can be more lenient there than a general compiler can. But what I want to focus on in my talk today is that we can do all of this by providing a really neat and concise high-level mathematical syntax to express these finite difference problems. So I'm showing here an acoustic wave equation with a dampening term. With a dampening term in the middle, eta, and I can express this in a single line of Python code. But before I get into the details of seismic imaging, I want to actually demonstrate a little bit of the basic principles of the Devito API on some much easier examples. For this, I'm going to use some examples from a very nice online resource from Lorena Barber's blog, CFD Python, 12 Steps to Navier-Stokes. Because it has very nice and clean examples, and everybody can read up on how to do these finite difference stencils. So the first example I want to look at is step 5 in the original tutorial series, linear convection in 2 dimensions. So we have du dt plus c times du dx plus c du dy, simple advection equation. And if we do finite differences, we end up having these, this is the discretized equation. It comes from the tutorial itself. So how would I do this in code? So we start with Devito by creating what we call a time data object, which is a special class of a range of classes that are effectively symbolic data objects. These serve 2 purposes. They have 2 roles. One, they are data carriers, effectively. They manage and allocate the user data, because for certain performance optimizations, you actually need to change the data layout in memory to make things faster. But their primary role in this example is they also behave like a perfect SciPy function. So I can do all the kind of things that SciPy allows me to do with them. I can take derivatives, etc. In fact, they also provide a few syntactic shortcuts like this here, u.dt, which is effectively an expression for the forward time difference on u. Same here, u.dxl is the left derivative, so the backwards difference for dx. Because we're using a backwards differencing scheme in this example as the original tutorial does. And so I can effectively write my governing equation just in this form, which is pretty much the top line. And what it will do under the hood for these shortcut notations will actually expand the finite differences, these little terms here, in a symbolic fashion. But I can then use SciPy solve utility to rearrange my stencil so that I have this structure where I update the forward stencil point in time, because this is how I actually run this. This is how I actually update my grid. It's just one line. Solve for the u.forward. And it creates the stencil expression for me. In fact, I don't have time to go through it in detail, but you can kind of see what the output of this is symbolically equivalent, making a few assumptions to this discretization from the notebooks. Now, what can I do with this? I again create a SciPy object, a SciPy expression object or equation object that updates the forward stencil point with the stencil. I do a little bit of bootstrapping to insert some spacing symbols. And then I create an operator. The operator is the other really important class in Devito because it encapsulates the entire code generation and automation toolchain. What this will do, it will take one, in this case, or in other cases, several SciPy expressions, and it will, in an iterative process, much like compiler passes, it will iteratively lower the complexity of these expressions down to actually raw low-level C. We'll resolve grid indices, we'll add loops into those, we'll optimize the loop nest structure to make these things really fast. And we compile the C code, load it up again, and it just all becomes and to execute this, it becomes just a function call that I can run in my Jupyter notebook. Before I can do this, I have to set up an initial condition. Again, as I said, the function u also has a secondary role as a data carrier, so it provides the property u.data, which just looks like a NumPy array to the user. We can set by our initial condition on this. We're using a smooth initial condition in this example because it avoids some of the numerical artifacts. And we can run this through our operator for 100 time steps, and my initial velocity wave moves to the right, which is pretty much the same result as we get in the tutorial. So for the next example, what I want to show is how we deal with boundary conditions. And so for this, I'm going to look at step 9 in the original tutorial series, the Laplace equation, which is a steady-state heat problem, quite well known again. And it's just this nice little heat equation with the 5-point star stencil that we looked at in the beginning. But this time, we need boundary conditions to drive the problem. In this particular example, we don't have a time derivative, so I have to actually manage the buffers myself. So I create two symbols, P and Pn, which behave pretty much like the ones we've just seen. But this time I need a second order derivative, so I set the space order to 2. Note though that this is just a parameter. I could have set this to something much, much higher. With space order 2, I get my nice 5-point star stencil, but I could have easily set space order 12 or space order 24, and I would have gotten a really, really, really big star stencil. Effectively, this parameter deals just dictates how big a discretization these shortcut notations then do. So Pn dx squared and Pn dy squared effectively create this. And I do the same trick again. I use SciPy to rearrange my equation and to get the discretized form and generate this update equation that I can feed into my operator. But now I need a little bit more. I need my boundary conditions. So for this example from the tutorial notebooks, we have this initial setup at the top where we have a slope on the right-hand side that is prescribed, and we have a prescribed Dirichlet boundary condition of 0 on the bottom as well. And we even have Neumann boundary conditions where we prescribe derivatives on the left and right-hand side. And I have to admit here, we don't actually have nice high-level symbolic abstractions yet for boundary conditions. We're planning to add some, but we actually have a much more powerful mechanism to deal with these. And this is actually born out of necessity because in most scientific, real-life science applications, you deal with all kinds of customizations which people need in their operators to do fancy stuff so that their science works. So what we've actually done is we've hijacked this hierarchical code generation process to expose a secondary layer API. And people who know SciPy a little bit will know this little bit of technicality here. So P itself behaves like a function object, so it has round brackets, it knows about dimensions. But if I go p.indexed, I get this cast into an index space object, which effectively represents a matrix access. So I have square brackets, I can then be explicit, I can use actual indices. So what I can do with this is that I can give this dimension x and a value 0, which means apply this function over all in x and 0 in y. So for all x and y equals 0, set the value 0. This is my bottom Dirichlet boundary condition. And if you mentally replace this x with a colon operator, that's effectively NumPy. Vector notation. So with this, I can express my boundary conditions. I can write my own convergence loop. I have to switch the buffers, which I can do by keyword assignment. And I can, again, recreate the original tutorial. Now let's have a quick look at a nice example from Seismic Imaging, so some real-life science that's run on really big machines, really big computers. So the idea is that we want to derive an image of the Earth's subsurface, the topology of these rocks and sediments under the ocean. And what people do in real life is they go out in a boat and they create a big bang, a big wave that runs through first the ocean and then these various layers and reflects, and they capture the reflected wave with lots of microphones that they trail behind the boat. And they do this over and over and over again, create really huge data sets which we can use to solve a PDE-constrained optimization problem. So this is where this becomes really huge compute, because you have to not only run this PDE once or twice, you have to run it hundreds and thousands of times. So for this, we need two operators. One, the wave propagation operator that effectively models how this wave propagates from an initial guess of this topology. And two, the so-called adjoint operator, that when we take the misfit or the residual against the actual data that we get from these ships, propagates this information backwards to give us a gradient in our optimization space. Now there's a technicality here, and that is that all these microphones and the source term here are sparse points. So again, I can utilize my low-level API to really get around these real-life science problems and inject really complicated sparse point interpolation routines in a symbolic form, so that the Devito operator still recognizes them and generates the right C code for it. So here's a forward operator for these large-scale seismic inversion operations in less than 20 lines of Python code. So we create our wave field U. We write down our primary governing equation with a Laplace term, a dampening term at the end, eta u dot et. We again let SciPy do all the heavy lifting on the symbolics, generate an update term. Here in red, I'm showing I've hidden some of the really nasty bits of these sparse point interpolations that become really big expressions. So we just create them in a symbolic form again. These terms we can chain them up to the stencil updates and create our operators. Now I need an adjoint, and there's a little trick here because I've used the acoustic wave equation, which is effectively self-adjoint, except for the dampening term. So in this slide, I'm showing in red the complete diff to the previous slide, and there's a sneaky little minus sign here because I have to invert the direction of the dampening term to actually get the adjoint of this equation. I've also renamed my field V instead of U, and I need to change a little bit the time discretization to run backwards in time here and on the time axis. I also change the way I insert my waves because I now actually insert the difference between the readings and the previous modeled output at the receiver locations. And then when I run backwards in time, I can create my gradient field, which is what you feed into these big seismic imaging algorithms. Because then the high-level math optimizations start to play. So here, I'm not going to go into too much detail of it. This is effectively, I ran this, one of my collaborators actually created this with an IPython notebook and less than 200 lines of Python code. It's an actual full-scale reverse time migration algorithm, which is one of the algorithms that runs on one of these really, really big machines. It's on a synthetic data set, Marmusi 2D, which looks very pretty. We create some synthetic data from it with our forward operators, smooth the topology, and then try and invert that smoothing, this perturbation that we've introduced here in an image. And this is the image on the left that we actually get. So this shows that this actually works in a kind of seismic context. And if I have enough time left, I want to have a quick word about performance. So these acoustic operators that we've just shown are notoriously memory bandwidth bound. We're setting on the roofline at around 60% of achievable peak, which is quite reasonable given the performance optimizations that we do. But the thing that's really worth noting here is that I can parameter sweep my discretizations. I can do this for varying stencil orders, 4th order, 8th order, 12th order, 16th order. There's some more cool stuff happening. We're trying to integrate some more powerful stencil optimization backends like this YASK, yet another stencil kernel, which is an Intel product. It's a pure stencil optimization DSL that doesn't know anything about finite difference math, but is really, really good at making stencil kernels fly, and it's better than our backend. We're trying to build this as another backend. And quick summary, so we've created Devito, which provides high-performance finite difference operators via DSL, and that is meant to increase productivity by providing a really high-level mathematical API to people. And with that, I'd like to thank you for your attention. I'd like to thank the SciPy guys for a really awesome package that allows us to do powerful stuff. And I'd like to thank Lorena for a wonderful tutorial that allows me to demonstrate this in a very neat fashion. So thank you very much.
Questions?
Yeah.
This is an example of migration, right? Seismic migration?
Yeah. Yeah, sorry, I had to brush over this a little bit. Yeah, we do reverse time migration. We also have FWI codes and things like that. But we're working on the seismic side further and further. There's more stuff to come. Yeah. In the back. Oh, Aaron.
Yeah, I think you briefly mentioned this, but how does this differ
From Phoenix, so from Phoenix it differs because it's finite difference. In fact, yeah, Phoenix is finite element, and this is finite difference. And in fact, this whole project is very much inspired by Phoenix and Firedrake and these type of things. So we're trying to do the same thing for a different branch of mathematics, effectively. So yeah, imitation is the highest form of flattery, I guess. Yeah, thank you.
So when you go to do the code generation, what are some of your pain points? I'm glad you laughed there.
So we do manual code generation. I know we're brave.
Okay.
Most of the pain points are actually the optimization. So we effectively build our own internal representation. We have like an AST of loops and things like that. And these things become very complicated to optimize. So it's not so much for the generation of the actual C code, we use some tools. Andreas Klöckner has a few things that are very useful. Yeah, and it's all just put together. But the actual optimization is much harder than the generation of the code. Yeah. Yeah.
So I'm curious, I was seeing you had the U.forward and so on, and I was thinking that was referring to forward versus backward Euler integration, but it looks like your backward is propagating backwards in time.
It's
Do you
both.
have the ability for doing explicit or implicit solutions? And if I want to do mixed, then how do I
So no, we're planning on doing mixed and implicit. We currently don't. So this is currently very much geared towards purely explicit stencil codes, because this is what we really can optimize quickly. There is a long-term plan to do to integrate with a solver for implicit and semi-implicit things, but not yet. Early days. Okay.
Last question.
Short question. I'm just curious, like 12th order, do you see numerical rounding at that point? Personally, at 7th order, so after that double precision, I haven't really given anything.
Oh yeah. So okay. So ramping up to 12th and 24th order, yeah, it's a bit of a trick. So the actual analysis of where do you have the numerical gains, that's a different story. The point is we can. And you can do you can do actually the analysis of where your round of order kicks in a notebook, rather than having to spend weeks to code it. That's kind of the point. Okay, thanks.